Hello and welcome back. In today's video, I'm overclocking the Orange Pi 5 Max 16GB all the way up to 2650 megahertz. I do that by overvolting the PVTPLL, and I also have to build my own clocking tool and my own telemetry tools. So quite a bit of work. I cover 4 distinct overclocking strategies ranging from pretty simple to quite advanced. However, before we jump into the overclocking, let's first have a look at the hardware and the software that I'll be using in this guide. The Orange Pi 5 Max is a single board computer featuring Rockchip's flagship RK3588 SoC. Rockchip primarily caters to edge compute and multimedia device makers, but also sells to SPC and development board companies like Banana Pi, Raja, and Orange Pi. The RK3588 is an 8nm SoC launched in 2022, succeeding the RK3399. It features 3 distinct core clusters, one quad-core cluster with ARM Cortex-A55 cores, and 2 dual-core clusters with ARM Cortex-A76 cores. The A55 cores have an advertised maximum clock frequency of 1.8 GHz, and the A76 cores can boost to 2.4 GHz. The RK3588 also integrates the ARM Mali G610 GPU and a dedicated NPU. The Orange Pi 5 Max features 4, 8, or 16 GB of LPDDR5 memory rated up to DDR5 5500, which translates into a peak memory bandwidth of 22 GB per second. The Orange Pi 5 Max supports plenty of external peripherals via various bus interfaces, including a x4 PCIe Gen 3.0 slot. The system we're overclocking today consists of the following hardware. Preparing the Orange Pi 5 Max for this guide is a little bit different than what we're used to with our typical x86 Windows-based systems, and that's primarily because of how the boot process works. There are essentially 3 stages to the boot process. First, a primary bootloader stored on the SoC's internal ROM or boot ROM initializes the CPU cores and very basic SRAM access, and it detects the boot devices such as SPI flash, eMMC, SD card, or M.2 NVMe. Then the secondary bootloader on the SPI flash initializes the LPDDR memory and loads the next stage, which is typically a U-boot from the SPI itself or an external storage device like the SD card, eMMC, or M.2 NVMe. Finally, the tertiary bootloader or the U-boot handles further device configuration. It loads the Linux kernel and starts the operating system. And then there is the question of Linux kernel support. In theory, there is mainline support for the Orange Pi 5 Max and its Rockchip RK3588 SoC thanks to the efforts of Collabora. However, the support isn't complete and it looks like booting from the M.2 drive isn't supported yet. Of course, I want to use the M.2 NVMe because it provides the highest performance. Luckily, Orange Pi also provides a few standard images on their website, but beware that these are based on heavily modified older Linux kernels. For example, the Debian Bookworm image is based on Linux 5.10. I picked the Debian Bullseye desktop image, which is based on Linux 6.1. You can read through the Orange Pi 5 Max user manual to find out how to get the image on the device. I found that the easiest method is to use the provided RKDev tool explained on page 53 of the user manual. A couple of notes. To enable the English interface, open config.ini and set selected equals to under language. Make sure to load the PCIe config file for the mini loader, and you need to know that the flashing process is pretty slow since all data is transferred via the USB interface. After the process is finished, the Orange Pi should automatically boot up. The default credentials are Orange Pi, Orange Pi. Of course, you can immediately update the packages using apt update and apt upgrade. Now we're ready for benchmarking. Pro tip, I also prepared an eMMC and SD card drive with Debian Bookworm server. Because the eMMC and the SD card are prioritized in the boot process, it's an easy way to recover the system if I overclocked too much on the NVMe drive. We use Debian Bullseye with Linux kernel 6.1.43 and the following benchmark applications to measure performance and ensure system stability. I mostly use the command line terminal to run these benchmarks, so it's not as easy as on Windows. I'll put up a how-to for the benchmarks on my blog if you want to run them as well. Note that we run the default configuration from Jeff Geerling's Orange Pi 5 Max review for the high-performance LinPack workload. Also, OpenArena runs on the CPU cores using LLVM pipe due to some issues operating the Mali GPU in OpenGL. GL Mark II ES2 is, however, running on the Mali GPU. And while I picked S2 as the stress test, it's not the worst case workload. It uses significantly less power than AI Benchmark or Jeff Geerling's high-performance LinPack benchmark. I use the following tools to flash the drives, log telemetry, and adjust clock frequencies. A quick couple of words on my telemetry tool. Basically, what we need to know about system telemetry is that the software doesn't always tell us what's going on with the hardware. So we have to be very careful when we look at telemetry. And that's particularly relevant for the operating frequency, voltage, and temperatures. For operating frequency monitoring, I rely on the data from the Rockchip RK3588 Technical Reference Manual, or TRM. We can access a lot of registers, including those for accurately calculating the operating frequencies of various IP blocks. I want to give a quick shout out to Willy Tarot, the creator of the CPU frequency measurement tool appropriately called Megahertz. It's a simple but incredibly useful tool that runs long loops of XOR operations that run at a rate of 1 operation per clock cycle. That gives us an easy way to indirectly measure CPU frequency and helps us validate that what we're seeing from the CPU registers is the actual CPU frequency. Also, a quick shout out to Boogie Pop, or HBIYIK, for sharing his MMM tool with the Raja community. This tool also accesses the SoC registers and was a great help to verify data when I was building my tools. For operating temperature monitoring, I rely on the information from the sysclass hardware monitoring directory. This maps directly to the 7-channel temperature sensor ADC of the RK3588. For the operating voltage monitoring, I rely on the information from the sysclass regulator directories. This provides information about the configuration of the 3 voltage regulators, the RK806 PMIC, and 2 RK860s. Unfortunately, it looks like neither of the voltage regulators supports real-time telemetry via the I2C interface. So the only way to verify the voltage in real time is to measure from the PCB. I mapped out the voltage measurement points in case anyone is interested. Just like the Raspberry Pi 5 telemetry tool we built a while ago, this tool supports logging to a CSV file for further analysis. Before we start overclocking, of course, we have to check the performance at default. The default operating frequencies for the Orange Pi 5 Max are as follows. A quick word on the frequency of the Cortex A76 clusters. While it's advertised to run at 2.4 GHz, its highest operating performance point, or OPP, is only 2256 MHz. This is a known issue for RK3588 based devices, as different SPCs may have a different maximum frequency. Furthermore, the actual operating frequency is determined by an adaptive clocking technology called PVTPLL, where PVT stands for process voltage and temperature. That means that it's not actually running at 2256 MHz. I'll cover this in depth in overclocking strategy number 3. Here's the benchmark performance at stock. When running the S2E stability test, the average A55 cluster clock is 1772 MHz with 0.95 volts. The average A76 cluster 0 clock is 2209 MHz with 1 volts, and the average A76 cluster 1 clock is 2252 MHz with 1 volts. The average SoC temperature is 37 degrees Celsius. The approximate wall power consumption is 10 watts. In the first overclocking strategy, we're not actually increasing the operating frequencies. Instead, we have a look at the performance governors and how to optimize them so that they give us maximum performance. Performance governors allow various IP blocks to adjust the operating frequency and voltage depending on the workload needs. Since Rockchip, the vendor of this RK3588 SoC, primarily caters to mobile and embedded devices, the performance governors are set up in a way that they balance power consumption and performance. But for us, what we want is maximum performance. The Orange Pi 5 Max has governors for the following IP blocks. I first became aware of the importance of optimizing the governors for SBCs by reading through T. Kaiser's extensive preview of the RK3588 based Rock 5B SBC. I strongly recommend checking out his SBC bench tool to better understand the importance of tuning the governors. Checking the configuration of the governors is pretty straightforward using the following commands or using my telemetry tool. Configuring the governors for maximum performance is actually pretty straightforward. Simply echo performance or always on. Each of the IP blocks should now be running at its highest performance setting, with the trade-off being increased power consumption. For my system, I actually always want the governors to be in maximum performance mode. So in order to not have to always type in the commands myself, I created a small service to do this for me. And here's how you create this small service. First, create a file with the following commands in bin called OPI5perf. Then create a service to execute our governor demands in the etc systemd system directory. Call it opi5perf.service. Then we can enable the service using sudo systemcontrol enable opi5perf.service. You can try out the service by starting it, or you can just reboot the system. If there are any issues, you can always use the journal control-xe command to check. So after reboot, the performance governors should be configured automatically. For your convenience, I also uploaded these files to my GitHub page. We rerun the benchmarks and check the performance increase compared to the default operation. While we're not exactly increasing the operating frequencies, adjusting the performance governors does have a decent impact on performance. Most notably, the memory and storage performance, which impacts GPU render workloads. The geomean performance improvement is plus 3.67%, and we get a maximum improvement of plus 35.92% in GL-Mark2 ES2. When running the S2E stability test, the average A55 cluster clock is 1772 MHz with 0.95 volts. The average A76 cluster 0 clock is 2206 MHz with 1 volt, and the average A76 cluster 1 clock is 2250 MHz with 1 volt. The average SoC temperature is 38.6 degrees Celsius, and the approximate wall power consumption is 12 watts. In our second overclocking strategy, we are increasing the operating frequencies, and we start by overclocking the memory. The dynamic memory interface, or DMC, of the Rockchip RK3588 SoC supports LPDDR4, 4X, and 5. LPDDR4 and 4X can go up to DDR4 4267, and the LPDDR5 can go up to DDR5 5500. Furthermore, the SoC also supports up to 32 gigabytes of memory. It also supports a wide range of timings, but these are set at boot and we can't manually adjust them. That last part is crucial for our overclocking efforts, as the memory configuration is provided by Rockchip as a binary blob, which we are not able to fully change. Based on the DDR binary blob, the DMC governor builds an operating performance point, or OPP table, similar to how it works for the CPU cores. We can check the table using the same command from before. In my case, it seems the available memory frequency options are 534 MHz at 725 mV, 1320 MHz at 800 mV, and 1968 MHz at 875 mV. Again, the maximum frequency can differ between RK3588 devices. Now, Rockchip provides a DDR bin tool that enables limited configuration of the memory via their GitHub page. You can refer to the DDR bin tool user guide for more information. Fortunately, BoogiePop developed a tool called RKDDR, which provides a simple interface to adjust these settings. So increasing the memory frequency consists of two steps. One, we add the operating performance point, and two, we manually increase it to 3200 MHz. Adding this OPP or operating performance point isn't that complicated, but it's still good to have a thorough understanding of how everything works. So for the purpose of this guide, I'll walk you through the entire process. First, we must understand how an OPP table is built. For that, we have to find the device tree of this device. A device tree is basically a file that describes the hardware structure to the Linux kernel. It's used very early in the boot up process, so therefore we have to look for this device tree in the boot directory. For the Orange Pi 5 Max, we first check the boot.cmd file to understand how the DTB is loaded at boot. So we navigate to the boot directory and open boot.cmd. Here we find two important lines. The first line tells us there's a text file called orangepie.env.txt, which contains some configurable parameters. The second line tells us the parameter fdt file is used to pinpoint the DTB file. Now we can check the boot orangepie.env.txt document to find the relevant DTB information. You'll find a line that says fdt file equals rockchip and so on .dtb. So let's check the files in the folder boot/dtb/rockchip. Here we can find several device trees for various Orange Pi 5 devices, including the one for our Orange Pi 5 Max, RK3588-OrangePi-5-Max.dtb. The DTB file is a binary file, which means we can't directly read its contents. However, it's pretty easy to convert the binary DTB into a readable device tree source or DTS file with the device tree compiler tool using the following command. In this command, -I is the input file type, -O is the output file type, and -o is the output file name. The output is a DTS file, which we can now open using any text editing software. The DTS file contains all the information about our hardware, or at least that's the idea. For development boards, the device tree is often incomplete or inaccurate and requires help from the open source community to get patched. Also note that the device tree configuration can differ between Linux kernels. For example, in the latest stable Linux kernel, 6.15.9, you'll find that the device tree for the Orange Pi 5 is split into multiple trees using #includes. So don't just blindly copy and apply the same modifications as I do for my device tree to your device. Make sure that the modifications are appropriate for your Linux kernel and your device. For this overclocking strategy, we're interested in the DMC configuration. We find two relevant data structures, DMC and DMC OPP table. The most interesting lines of the DMC structure are operating points V2, which tells us there is an OPP table linked to the DMC, and center supply, which tells us what voltage regulator is powering the DMC. The hex code in brackets provides a reference to the P handle or a pointer that defines the node. In our case, operating points V2 links to 47 hex and center supply links to 48 hex. A quick search for those handles tells us that operating points V2 links to the DMC OPP table and center supply links to the VDD DR S0 voltage supply. Let's have a closer look at the DMC OPP table, where we can find multiple OPP nodes. You can learn about the various parameters from the kernel.org documentation. The long story short is that each node defines an operating point by a number of parameters, including but not limited to voltage, frequency, and current. There are two ways to modify the device tree. Either we modify the device tree source and then recompile the device tree binary, or we make use of a device tree binary overlay. Usually either one of these two methods will work, although there are situations where you really have to recompile the entire DTB. For the purpose of this guide, I'll show you both options. To add a performance point for our target frequency of LPDDR5 6400, we can either add a new OPP or modify an existing one. You'll find that our device tree already has a higher OPP than the frequency we're running currently. We have an OPP at 2750 MHz instead of 1968 MHz. So we can copy the entire OPP for 2750 MHz and paste it right below. Then we change the following values. Of course, we change the name, and we also change the frequency, and make sure to change it in hex values. Then let's save this as a new DTS file. Now we can recompile the DTS into a DTB using the following command. Next, we can place the new DTB file into the boot DTB Rockchip directory. And lastly, we can update the DTB line in the boot orangepie env.txt text file. To keep track of changes, I prefer to comment out the original line and add a new line with the modified device tree link. Then save the file, reboot, and after the reboot you'll find that the frequency increased, but not to the 3200 MHz we intended. I'll address that in just a minute. To create a new performance point using a device tree overlay is also pretty simple. We have to create a text file called RK3588 DMC3200.dts with the following content. You'll find that the content is the same as the regular DTS file, but shorter. With an overlay file, we're simply referencing a specific device node and adding a new OPP entry. Now we can recompile the DTS into a DTBO using the following command. As you can see, the command is almost identical to the one for compiling a DTS into a DTB, except for the file extension of the output file, which is now a DTBO. Now we need to place the DTBO file in the right folder. To figure out which folder, we can check the boot command file again. This is the relevant line. The first line tells us there's a parameter called user overlays, which lists user-made overlays to be used at boot. The second line tells us the overlay files should be saved in the boot/overlay-user directory. So first we have to make sure the directory exists, and if not, add the directory. We can simply open a terminal in boot and then type the make dir command. Next, go back to the folder where you saved the DTBO file. Open the terminal again and copy the DTBO in the newly created overlay-user directory. Next, open the boot orangepie env text file and add the following line. Make sure to activate the FDT file line of the original DTB, since that's the file the DTBO references. Save the file and reboot, and after the reboot, again you'll find that the frequency increased, but not to the 3200 MHz we intended. We'll address that right now. The final step of this overclocking strategy is to enable the higher memory frequency. And as I mentioned before, there are two ways to do it. The hard way using Rockchip's DDR-bin tool, or the easy way using BoogiePop's RKDDR tool. And I prefer the easy way. First, clone the GitHub project to your drive, and then open the script. Browse to LP5 and set the first line to 3200. Then exit the application and confirm the settings with Y. Then reboot the system. And after the reboot, you can check the clock summary or my telemetry tool to verify the DMC is now running at 3192 MHz. We rerun the benchmarks and check the performance increase compared to the default operation. Similar to our x86 overclocking adventures, increasing memory performance helps improve performance in memory-sensitive workloads. The performance of the integrated Mali G610 graphics also improves noticeably. Looking at the memory performance, adjusting the memory frequency specifically improves the latency. The geo-mean performance improvement is plus 8.26%, and we get a maximum improvement of plus 52.82% in GL Mark II ES2. Here's the memory bandwidth scaling with various DMC frequencies. When running the S2E stability test, the average A55 cluster clock is 1772 MHz with 0.95 volts. The average A76 cluster 0 clock is 2206 MHz with 1 volts, and the average A76 cluster 1 clock is 2249 MHz with 1 volts. The average SoC temperature is 38.7 degrees Celsius. The approximate wall power consumption is 12 watts. In the third overclocking strategy, we finally get to increase the operating frequency of the CPU cores by using Rockchip's PVTPLL adaptive clocking technology, which requires us to overvolt in order to overclock. Let's have a closer look. Rockchip filed a patent for its adaptive frequency technology on March 21st, 2018. The patent describes a self-adaptive frequency tuning circuit that automatically adjusts the frequency output in response to process, voltage, and temperature changes. Experienced overclockers will immediately think of AMD's voltage adaptive operation technology, which also adapts the clock frequency to the operating voltage. The RK3588 SoC supports 6 PVTPLLs for the following IP blocks. You can monitor the PVTPLL frequencies using my telemetry tool. As I mentioned before, you'll find that the actual operating frequency is not the same as the available frequencies in the OPP table. In fact, you'll find that the operating frequency is determined entirely by the operating voltage, even though it might seem that it is determined by the OPP table. The easiest way to illustrate this is by creating an OPP table with just 2 points, 1200 MHz at 850 mV and 1800 MHz for the A55 and 2256 MHz for the A76 cores at 900 mV. The expected behavior is that the CPU clusters would operate at 1200 and 1800 and 2256 MHz respectively. However, the reality is that they work at totally different frequencies. 200 to 300 MHz higher at 850 mV and 100 to 200 MHz lower at 900 mV. The bad news is that we can't rely on a traditional method of adding OPPs to increase the operating frequency. But the good news is that we now have a clear path to increase the operating frequency. We just have to overvolt. Now, before we start overvolting, let's first have a closer look at the voltage topology of this Orange Pi 5 Max single board computer. The Orange Pi 5 Max voltage topology consists of one RK806 PMIC and two RK860 step-down DC-DC voltage regulators. The PMIC takes care of the vast majority of the voltage regulation, whereas the DC-DC regulators specifically cater to the two Cortex A76 clusters. The voltage regulators are clearly structured in the device tree, and it's relatively easy to figure out the different configuration parameters. Let's take VDD CPU Big 0 for example. V in supply tells us that there's a 5 volt input voltage for the regulator. The regulator min microvolt tells us that the minimum voltage is 550 millivolt. Regulator max microvolt tells us that the maximum voltage is 1050 millivolt. And the P handle tells us that this regulator is linked to CPU nodes 400 and 500. Increasing the operating voltage isn't that complicated, but again, I'll walk you through the process so you understand how we get there. For this strategy, we focus on the voltage rails that power IP blocks with PVTPLL clocking. From the RK806 and RK860 datasheets, we find the following specifications. Based on this, I decided to set the regulator max microvolt for every rail to 1.5 volts. Then, to make sure we can use the additional voltage headroom, we must also update the OPP tables. Here I configure the CPU clusters and GPU to allow up to 1.5 volt. We can do that by changing the third and sixth value for each OPP microvolt to 1.5 volt. To make my life a little bit easier, I created a new unlocked device tree based on our modified DTB from OC strategy number 2 using the following modifications. I also share this on my GitHub page. The next step is to actually go and try higher voltages. For this, I create 2 device tree binary overlays, one for the CPU cores and one for the GPU, so I can enable them separately. This is my template for the CPU core PVTPLL overvolting device tree overlay. And this is the template for the GPU PVTPLL overvolting device tree overlay. Before we start experimenting, make sure to move the unlocked DTB and overclock DTBOs to the appropriate folders, and add the appropriate lines to our orangepie.env.txt configuration file. To keep the testing simple, I just created a bunch of device tree binary overlays with various voltages and then tried to enable them one by one. For the CPU cores, I found that the limiting benchmark was Jeff Geerling's high performance LinPack benchmark. With the Raspberry Pi 5 official USB Type-C power supply, the Orange Pi 5 Max would shut down at around 33 watt from the wall socket. With the Kenengjia USB Type-C power brick I got together with the Orange Pi 5 Max, I see up to almost 40 watt power draw. That's with 1.3 volt for the A76 cores, 1.25 volt for the A55 cores, and an operating temperature of about 70 degrees Celsius. For the GPU, unfortunately, I didn't find a more stressful workload than GL Mark II ES2. I could increase the GPU voltage to 1.1 volt. I did spend a little more time trying to figure out higher voltages to map out the VF curves. The A76 cluster 0 can get all the way up to 2669 MHz at 1.4 volt. A76 cluster 1 gets to 2759 MHz at 1.475 volts. The A55 cluster can get up to 2123 MHz at 1.25 volt, and the Mali G610 GPU can get all the way up to 1.5 GHz at 1.25 volt. We rerun the benchmarks and check the performance increase compared to the default operation. Obviously, increasing the CPU core, DSU, and GPU operating frequency has a direct impact on the benchmark performance, and we see improvements across the board. The geomean performance improvement over stock is now plus 27.23%, and we get a maximum benchmark improvement of plus 75.92% in GL Mark II ES2. When running the S2E stability test, the average A55 cluster clock is now 2099 MHz with 1.25 volts. The average A76 cluster 0 clock is 2556 MHz with 1.3 volts. And the average A76 cluster 1 clock is 2601 MHz with 1.3 volts. The average SoC temperature is 52 degrees Celsius. The approximate wall power consumption is 21 watts. In the final overclocking strategy, we try to override the PVTPLL frequencies by manually tuning the frequencies. For this, I had to build my own overclocking tool. The Rockchip RK3588 SoC uses a 24 MHz crystal oscillator as a source for the clock tree. This is the source for the 18 PLLs used by the SoC to clock the various IP blocks. The PLLs include several general PLLs used across the SoC and specific PLLs for specific IP blocks. Each IP block typically has a number of clock sources to choose from. I developed a tool that can configure many parameters related to the clocking of the RK3588, including the CPU cores, DSU, GPU, and NPU. It has options for both the PVTPLL as well as non-PVTPLL clocking methods, which I'll cover in just a bit. Again, I'll share the code on my GitHub so you can try it out as well. Please be aware that this is a very advanced tool, so don't use it if you're not comfortable with the risk that you might damage your hardware. Also, the tool is kind of still a work in progress. I use it for my purposes, but there might be some bugs here and there, so please be careful. Generally speaking, there are two methods to overclock the IP domains with PVTPLL support. You can tune the PVTPLL, or you can use a different PLL. We already figured out that we can increase the operating frequency by increasing the operating voltage, as the adaptive clocking technology, PVTPLL, scales the frequency with the voltage. This is very similar to AMD's voltage adaptive operation, or more commonly known as precision boost. Unfortunately, we don't have as many OC tools available for PVTPLL tuning as we have with, for example, AMD's curve optimizer. As far as I can see, there are two options for tuning the PVTPLL. We can change the oscillator type, and we can adjust the oscillator ring length. The oscillator type lets us swap different oscillators to generate the frequency. For example, for the CPU cores, we can pick between 6 types of oscillators. I don't quite know how to decode these oscillator types, unfortunately. The oscillator ring length determines the number of stages in the oscillator ring. The more stages, the longer the signal delay, and so the lower the operating frequency. Both parameters work in tandem as they affect the signal delay through the oscillator circuit and ultimately the clock frequency. Let's take big core 1 as an example. At 1 volt, the operating frequency ranges between 2072 and 2330 MHz depending on the oscillator type. Then, with the default oscillator type, the frequency ranges between 735 MHz with a ring length of 63 and 2272 with a ring length of 10. All CPU cores and the DSU have the same 6 available PVTPLL types, whereas the GPU and NPU only have 2. For the GPU, here's the operating frequency at 1.1 volt with each type of oscillator. The maximum frequency is slightly over 1.4 GHz. Unfortunately, I couldn't quite get that much extra frequency from PVTPLL tuning. Changing to a different oscillator type wasn't really stable, and only for the GPU I was able to reduce the ring length by 1 step. That gave us an extra 40 MHz, bumping up the clock from 1365 MHz to 1405 MHz. As I explained when we covered the RK3588 clocking topology, for each of the PVTPLL domains, there is also an alternative, more classical approach to clock configuration derived from a crystal reference clock. You can find the various tunable parameters in my clocking tool as well. Let's take two examples, Big Core 0 and the GPU. The Big Core 0 operating frequency is decided by a multiplexer or MUX, selecting between 3 clocking options, UC, Clean, and PVTPLL. I don't know exactly what UC stands for, maybe universal or user clock, but that's the clock we pick when manually controlling the output frequency. The UC clock itself is a function of the selection of one of 3 available clock sources, slow, GPLL, and B0PLL, which then gets divided by a core-specific UC divider. Slow, in this case, means derived from the 24 MHz crystal and is used for idle or sleep states. GPLL stands for General PLL, and it is a clock source that's widely used across the many RK3588 SoC IP blocks. It's defined as running at 1188 MHz and is also derived from the 24 MHz crystal oscillator. Technically, we could adjust the GPLL frequency to run at a different frequency, but that would affect a lot of other parts of the SoC, so it's not recommended. B0PLL is a reference clock specifically used for the Big Core 0 cluster and the preferred source for our manual overclocking attempts. It is also derived from a 24 MHz crystal and uses one multiplier M with 2 dividers P and S to generate the final B0PLL frequency. For example, if M is 400, P is 2 and S is 1, then the calculation is as follows. The ultimate core frequency is then the 2400 MHz B0PLL divided by a core-specific UC divider. For example, if the divider is 2, then the core frequency will be 1200 MHz. The clock tree for big core 1 and little core clusters is very similar, with the exception that the reference clock includes B1PLL and LPLL respectively. All three reference clocks are also available to the DSU S-clock and P-clock, in addition to the GPLL. The GPU clocking is a bit simpler as it lacks a user-configurable reference clock. Instead, the GPU clock can be derived from several general clock sources available in the RK3588 SoC. After selecting one of the available reference clocks, the frequency gets divided by a GPU-specific divider before yielding the ultimate operating frequency. As I mentioned already, for the GPU, I was able to squeeze a little bit more frequency out of the PVTPLL technology. Unfortunately, for the other IP domains, there was almost no headroom left. Anything I changed caused freezes or instabilities. So for the CPU cores, for the A55 and A76 cores, I decided to try a traditional overclock using the UC dividers. And I did that using the same 1.25 and 1.3 volt as I used for the PVTPLL configuration. Unfortunately, it seems that the PVTPLL technology is pretty good at extracting the maximum amount of performance out of the CPU cores, because there was basically no headroom left. In fact, I couldn't even reach the same frequencies as PVTPLL. In fact, the A55 cores could only clock up to 1830 MHz, which is 150 MHz less than what the PVTPLL gave us at 1.25 volts. The A76 cores could clock up to 2520 MHz, which is 80 MHz lower for the big core 1 cluster. Now bear in mind that the PVTPLL technology is an adaptive clocking technology that will adjust the frequency according to the voltage and the temperature. So meaning it adjusts the frequency according to the workload intensity. If we run Jeff Geerling's high-performance LINPACK workload with the PVTPLL configuration from OC strategy number 3, we find that the A76 cluster 0 frequency drops all the way to 2518 MHz, and the A76 cluster 1 frequency drops to 2561 MHz. That makes our manual overclocking results seem a lot more reasonable. Upon opening the RK3588 SoC tool, we rerun the benchmarks and check the performance increase compared to the default operation. The slightly lower frequencies than our previous OC strategy translate into slightly lower benchmark performance, though still significantly higher than stock. We still have some slight performance improvement in the high-performance LinPack and GL Mark II ES2 benchmark. The geomean performance improvement over stock is plus 22.37%, and we get a maximum benchmark performance improvement of plus 76.48% in GL Mark II ES2. When running the S2E stability test, the average A55 cluster clock is 1830 MHz with 1.25 volts. The average A76 cluster 0 and cluster 1 clock is 2520 MHz with 1.3 volts, and the average SoC temperature is 52.7 degrees Celsius. The approximate wall power consumption is 21 watts. All right, let's wrap this up. A couple of months ago, I decided that this Orange Pi 5 Max should be my summer project because it would push me out of my x86 comfort zone. It's the second single board computer I've overclocked on this channel, following the Raspberry Pi 5 from last year. And I learned a lot during this project. I learned how to write my own clocking and telemetry tools. I got to play with the new PVTPLL clocking technology from Rockchip, which is the first time ever I've used that technology. And so I feel like the project was worth it from a learning experience kind of a point of view. Of course, there's still a lot left to learn, right? I want to run the latest Linux kernel, figure out how to do proper GPU acceleration, maybe have a look at the NPU. There's still a bunch of things that we can't read out in the clock tool, like for example on the memory side, but all of that will have to wait because the first thing I want to check is, of course, how this Rockchip RK3588 behaves with more exotic cooling. Anyway, that's it for this video. I want to thank you for watching, the YouTube members and the patrons for their continued support. Of course, I'll put up a written version of this video up on my blog as I usually do. I'll also publish most of the settings and the tools on my GitHub page so you can easily try it out for yourself. If you have any questions or comments, feel free to drop them in the comment section below, and see you next time.